everybody's ready, I suppose we can get started.
Yes, please.
Okay, so now for something not completely different, but a little different. So we're gonna have a little bit of a change of pace here. This section is titled Cerebras SDK for HPC Research and Applications, but I think HPC here is in some ways a little too narrow. The tools that I'm going to show you are really about kind of pulling everything apart and understanding at a very low level kind of the entire world of other things that you can do with our architecture. You know, we've talked a lot about the way that our software stack makes it incredibly easy to train very, very large models. We've also talked quite a bit today about sparsity. But what I'm going to focus on is some of the fundamental aspects of our architecture in a little bit more detail. The other sorts of applications that this can speed up, and how you can actually get your hands dirty with the architecture at a very low level to kind of break outside the box and program all sorts of other kernels for this device. So first, I know that you saw these slides before, but I think they're worth going through again to set the stage about what exactly this chip is, and then I'm going to go into quite a bit more detail about the architecture itself. So, you know, as you know, this chip, which is housed inside of our CS2, you know, the two systems that the ANL has hundreds of thousands of cores, and we say they're optimized for sparse linear algebra. You know, what we really mean by being optimized for sparse linear algebra is that they have very high memory bandwidth and they're great for operating on vectors. And you'll see an example of that further down. I won't talk about the CS2 as much. You've heard quite a bit about our wafer scale cluster. You know, the fact that this device and clusters of these devices are programmable via PyTorch, but I'll mention, you know, the part I'm talking about here today is our SDK, which gives you really low-level access to the system. So Sylvia presented this slide yesterday as well, but it'll set the stage for some slides that go in a little bit more detail about what really the implications are at a hardware and programming level of these features. So the way that the CS2 appears to a low-level kernel programmer is a giant logical 2D array of individually programmable processing elements. This is a significantly different model than, say, a GPU, which is, you know, in some sense a variation of SIMD, single instruction, multiple data, though, of course, the terminology that NVIDIA uses is single instruction, multiple thread. This is true MIMD, multiple instruction, multiple data. These are hundreds of thousands of independent cores, which support natively half and single precision data types. And data flow is the key word here. It's a data flow architecture, which means that chunks of code called tasks are activated or triggered by the arrival of a data packet. We call these data packets wavelets. They're just these little 32-bit packets that travel between these processing elements. And the way that these processing elements are actually wired together to communicate is over routes, virtual channels called colors. So each processing element has two bidirectional links to each of its neighbors and a bidirectional link called the ramp between its router and its processor. This part here, consisting of the processor and the memory, we often call the CE, or the compute element, but the whole thing together with its fabric router is called the processing element. So we have these virtual channels, which we call colors, which exist on top of these physical bidirectional links. And you can change the routing of these channels actually dynamically at runtime. They're also statically programmable at compile time. It takes a single cycle to send one of those data packets from the router of one processing element to the router of another, which means that you can get from one end of the chip all the way down to the other end of the chip in less than 2,000 cycles with a 32-bit packet. The other key feature, key enabler, and this is really the key enabler of sparsity in any form, is the 40 gigs of on-chip SRAM, right? There's no cache hierarchy at all. There's no cache, or in another way to think about it, there's nothing but cache. Each of these cores owns 48 kilobytes. That 48 kilobytes is the data and the instructions that processing element has. And you can read and write to that memory in a single cycle. So a bit more about the compute. As I mentioned, it's a data flow execution model, which means tasks are triggered by wavelets. A wavelet coming in on a specified virtual channel, the specified color, will activate a particular task. And like I said, a task is just a chunk of code. You can truly individually program each of these processing elements. What that means is that even though this would be inadvisable, if you wanted to, you could write 850,000 separate programs and load them on to each core. Like, these are truly individually programmable. There is some amount of asynchronous operation. So for the main part, these cores have a single main thread, non-preemptive main thread that is always running, and it's executing some task. But there are what we call micro threads. There are 8 of these on each processing element, which allow for some asynchronous operation. So for instance, say that you have some operation which is expecting to receive 8 wavelets on a certain color from your neighbor. Well, if those 8 wavelets haven't yet arrived to your processing element, that micro thread can go to sleep, and some other, the main thread, some other task can pick up and activate and start running. And once those 8 wavelets are available, that micro thread will wake back up and consume them. So they allow for some amount of concurrency, but they don't allow for parallelism on the cores. These cores are not parallel in any sense, but they do have some concurrency with these micro threads. One thing about this is it makes control flow fairly straightforward to reason about, particularly for such a large chip, which foreshadows one really important feature of our chip, which is that we have a cycle accurate simulator of the chip, and I'll talk about that later on. So a bit more about these routers and the communication. So as I mentioned, the PEs communicate to their compute element and to their 4 adjacent PEs via their routers. And this router is essentially just a 24 entry table with those 24 entries, each corresponding to a color. So there's a little example here of the piece of a table, of the transmit piece of the table. So we have 4 colors, this gray, green, blue, and purple. This green color has the ramp bit set. This blue color has the east and south bit set. This purple color has the north bit set. So what does this mean? Well, on this processing element right here, if we say, hey, I want to send a data packet out along the color purple, then what it's going to do is it's going to be sent up to the PE to the north of it. If I say, hey, I want to send out a data packet, a wavelet along the color blue, then it's going to be sent to the south and to the east. This is a really cool feature because this means that we can multicast without any sort of penalty or extra cycles. we can send a wavelet in multiple directions at once. This color here being set to ramp. This would be important if, say, this color green has its RX, its receive bit, set to east, and then it has this TX bit set to ramp. Then what would happen is, say we have a PE over here, which sends out on color green. The TX bit here for that color, the RX bit here for that color green is set to east, which means it's expecting to receive a wavelet along that color from its neighbor. And then this RX bit set to ramp, or this TX bit set to ramp means that it transmits it down the ramp. So this is going to be a color on which you expect to receive data from a neighbor. Kind of a natural next question is, well, we have all these data wavelets traveling across the fabric. How do we handle when there's a ton of contention for those physical links between processing elements? Like, say that we have 20 wavelets on multiple colors trying to cross the links and be ingested by a processing element. Well, we also have these little hardware input-output queues that sit between the fabric router and the compute element, which help alleviate those sorts of stalls, which we call back pressure. It basically is like a little holding area for wavelets to be ingested by the compute element or to be sent out to the fabric. So a bit about the memory, which, as I said, I think is the really big enabler for sparsity. And to make that point, I'm gonna duplicate a slide that you saw earlier today, and try to tie it into the story here. So as we've mentioned, there are 40 gigs of on-chip SRAM on this chip, and it's uniformly distributed on the wafer. Each one of these processing elements has 48 kilobytes of memory that is accessible by it and only it. Other PEs cannot address that memory. The PEs can only communicate via the fabric router. What's special about this memory, we say a single cycle for read and write. Really, it's more than just one read, one write per cycle. You can do 128 bits of reads and 64 bits of writes in a single cycle, which you put all that together. That's how you end up getting that 20 petabytes per second total memory bandwidth, aggregate memory bandwidth number. Of course, if you think about, what does it mean to be able to read 128 bits per cycle and write 64 bits per cycle? Well, say that you want to perform a half precision add. So you have two sources, a source 1 and a source 2, and you have a destination, DST. And all the operation is doing is source 1 plus source 2 equals DST. Well, source 1 is a 16-bit operand. Source 2 is a 16-bit operand. The destination is also a 16-bit operand. Like I said, this is a 16-bit add. But if you add that together, right, you only would need 32 bits of reads and 16 bits of writes in a single cycle to be able to read, perform the operation, and write all in one cycle. So what we have to actually take full advantage of that memory bandwidth is we do have a limited SIMD capability on these processing elements. And this is really the source of any true parallelism, so to speak, on the individual cores, is this SIMD capability. So you can perform 4 half precision adds in a single cycle. If you do the math, that's 128 bits of reads and 64 bits of writes. So by saying that I can do 4 half precision adds in a single cycle, that means perform the reads, do the operation, and write back to memory. So when we're talking about the number of cycles it takes to perform an operation on this architecture, we are talking about also reading the operands and writing the operands back to memory, which is a bit of a shift in how you think about what a flop means, what it means to do a single floating point operation. So I want to bring back up this figure, like I mentioned, because I want to emphasize this point. The reason that we are so good at sparsity is the fact that when you have a really sparse problem, effectively you have a dense, high compute intensity operation like a matrix multiply turn into a bunch of scalar vector multiplies. And these, of course, are very low intensity, or they're high memory bandwidth intensity. You need to read and write lots of bytes for each operation that you do. But because, for us, our operations are bound up with reading and writing to that memory, we can get full throughput, full performance out of our cores, even when we have very, very sparse operations like this. This is super valuable, particularly to a lot of scientific applications, particularly algorithms like a finite difference method, where sparsity doesn't mean 90% sparsity. Sparsity means 1 times 10 to the negative 6 or less elements in a constructed matrix, and I'll talk about a couple of those applications at the end. So what tools do we provide to actually get your hands dirty in the details of our architecture beyond using our really nice PyTorch stack? Well, for that, we provide what we call the Cerebras SDK. So this is a tool set meant to be a general purpose parallel computing platform and set of host APIs for writing custom programs for a CS2 and now CS3 as well. It's built on top of a language called CSL, the Cerebras software language. I'm going to talk in some detail about that language and how it actually allows you to control the hardware. And then it also provides host APIs in Python for writing your code on the host side that actually copies data to and from the machine and launches kernels on the machine. We also provide a growing set of libraries for the CSL language, which are meant to wrap up some very common sorts of computational motifs of kernels that people implement in CSL. We provide a variety of tools with the SDK as well. The most important in my mind is our simulator. So I probably do 99% of my software development in the simulator, and then I only run on a system once I really need to actually use the entire wafer and get real performance results. So with our simulator, like I said, it's a cycle accurate simulator because really in a lot of ways our architecture is fundamentally quite easy to reason about and simulate. Of course, because it is cycle accurate, when you're using the simulator, you're not usually running on a full size chip. You're running on a small chip. So here in the example on the right, this was a simulated run on a 6x6 little sub fabric, a 6x6 mini wafer. So often you'll think about your logic and problem mapping on maybe a 5x5 to 10x10 to 20x20 sub wafer and run that in your simulator. So what does this kind of paradigm look like from a programmer's perspective? Well, on your host CPUs, so this is a server attached to the CS2, or your own CPU or any x86 server that's connected to the simulator. You have, like I mentioned, APIs in Python. with C++ APIs for writing C++ host code coming by the end of this year. With these Python APIs, they're responsible for actually loading your program onto the simulator CS2 system, streaming in and out data, and for debugging purposes, directly reading and writing to the memory of the PEs. On the device side, that again is written all in CSL, which is that data flow programming language. If you think about it, this model is not too different than other network attached accelerators, right? It's not much different than, say, you writing a CUDA program for a GPU and then writing some host code in C++ or even Python that actually calls your CUDA kernels and makes your CUDA mem copy calls to copy data to and from the device. So I'm going to talk a little bit about our CSL language, what this looks like, the syntax, but then also give you a bit of flavor of what a program in this language running on the CS2 will actually look like. So there's a whole lot of features in our language that are just all of your standard expected, imperative procedural language features that are essentially straight from C via a language called Zig. So it is a C-like language for programming the individual processing elements, but with some of the niceness of Zig, which has some nice type-safe features. But then there's a lot of CSL specific features. And what I mean by CSL specific is features that are really for the purpose of that are really for the purpose of getting all of the performance possible out of the wafer and doing unique things for programming this wafer that you wouldn't be doing in just a normal programming language on a CPU. So in some sense, at least the level of programming and digital processing element, this is quite familiar to an HPC programmer who's familiar with a language like C. So in terms of familiar features, the language has a type system that's similar to a lot of other modern languages, Zig, of course, but also Go or Swift or Rust. We have half and single precision float types. We also have 16-bit and 32-bit signed and unsigned integers, and a bool type. All of your variable declarations are prefixed with either var if it's mutable or const if it's not mutable. We do have pointers as well, and we have arrays. Functions use the Zig style syntax, which is also the modern C++ style syntax of having a trailing return type. But if you look at this, actually, this you could take this function and it would work as is in Zig, and with a few changes to the syntax, this would compile in C as well. This is a pretty standard naive factorial function. Pass by value or reference and inlining automatically handled. What I really mean here is that basically everything is passed by value. If it's a pointer, right, the pointer itself is passed by value, but the underlying array is not copied. It's a reference via the pointer. So it's not a very complicated function syntax system. In terms of control structures, everything you would expect: if loops, while loops, for loops. We also have a for loop, both the C style for, but also the range for. That's kind of like the modern C++ range for loops. We also have a bunch of quality of life features, which are just things that make it, that you might not be super familiar with in existing languages, but are very important for kind of composability and compilability of our programs. We have this thing called comp time blocks. This is actually from Zig. So basically, you just wrap a whole chunk of code in this comp time block, and that just tells the compiler all of this needs to be evaluated at compile time. This actually can be useful for front-loading computation or even debugging. But it's very nice just to be able to explicitly wrap a whole chunk of code and say, all of this you should be able to evaluate at compile time and not at runtime. We also have this concept of params, which are a lot like defines in C. These are parameters that have to be bound completely during compilation. So what that means is, when a file is being compiled, these parameters must have been set before the file is being compiled. You can almost think of like, const expra in C++ or something like that. The point is that these operate a lot in the way that, say, a define in a preprocessor define in C would operate. We also have this concept of modules via Zig. So any CSL source code file can be a module, which can be imported into other modules, and thus other code files. So a module acts as an instance of a unique struct type, which means that you can import the same code file multiple times and it'll act as multiple modules. So I have an example here, this little piece of code called m1.csl. There's a global variable in the code called x, and there's a little function here called increment that just increments that variable x. I have another piece of code here where I've imported this module twice. And one, I've given it the name v1, the other I've given it the name v2. So this is the name of our module, v1 or v2. And then we can use this dot operator to access the functions or variables inside the module. So here I call v1.increment. And then on the next line, I call v2.increment twice. But because these are separate instances of the module, calling increment on v2 does not at all affect the value of x inside of v1, right? So after you run these two lines, v1.x will be 1 and v2.x will be 2. So moving into some of the features that really are about knitting all of these cores together on this data flow architecture. Another thing whose syntax comes to us from Zig is this idea of built-ins. These are kind of special functions. They all begin with an at, and these are language extensions without any special syntax. So these can invoke special compiler functionality. The simplest example is one right here. This at zeros, which is declaring a 4x5 matrix. This U32 should not be here. Sorry, I just redid these boxes and I accidentally pulled the U32 in. So ignore the unsigned 32 type here. This line is just meant to declare a 4x5 matrix of type F16, where all of the elements are initialized to zeros. Okay, so tasks. As I mentioned, right, this is a data flow architecture and it's built around tasks, which are just chunks of executable code. That's all they are, is chunks of executable code. They are the core chunks, the core building blocks of programming this architecture. There are two ways to trigger a task. We have this concept of local tasks, which are tasks which you at some point in your code just say, hey, I want to activate some other task when this task is done, and you call @activate, and then that chunk of code will run next. You also have data tasks or wavelet triggered tasks, which are the tasks who are activated, whose action is triggered by incoming data wavelets. So I have a little bitty code example here, and then I'm going to expand on it in a couple slides. But here we have a task named recav task, which is expecting as an argument unsigned 32-bit integer. We name this argument data. And all this task does is when it receives data, it's going to assign this global value that lives in our program the value in data. So tasks all have some associated task ID. A wavelet trigger task, right? Remember, I said that a wavelet trigger task, right? It's got to be associated with some color. There's some virtual channel that it's going to expect its data to arrive on. And when that data arrives, it's going to ingest that data and then operate on it in some way. So this task has an ID, which is related to the color along which it expects data. So whenever we receive a wavelet along the color, rec of color, this task is going to operate. It's going to take in that wavelet as a U32 argument, and it's going to set global value equal to that value. This set local color config call down here is basically telling our program that for this color, rec of color, we expect to receive data along this color from the west of us, and then we expect to transmit it down our ramp to our compute element. So what's going to happen in the action of this program is that some wavelet is going to come in from the PE to the left of us along the virtual channel rec of color. It's going to hit our PE's router. That router is then going to send it down the ramp where it is ingested by this task. And then the data that was in that wavelet's payload, that's what we set global value equal to. So the last key feature, and this is, I think, one of the most unique features of our processing elements, of our individual cores, this idea of data structure descriptors. So these are just a mechanism to bind together an array with some access pattern as a complete unit. Operations that use these DSDs will run for multiple cycles until that full instruction is complete. So let me try to explain what I'm talking about here. So here we have 3 DSDs: dest DSD, source 0 DSD, source 1 DSD. Each of these DSDs have some access pattern that's defined. If you look at dest DSD, what this access pattern is saying is that we have some array that we've declared previously in our code called DST. And this DSD is just going to access the first 5 contiguous elements of DST. This source 0 DSD just accesses the first 5 contiguous elements of source 0 array. And the source 1 DSD accesses the first 5 contiguous elements of an array named source 1. So when we do this f_add_h built-in right here, so f_add_h is a half precision add. So presumably these arrays, DST, source 0, and source 1, are of type F16. They have half precision floating point numbers. And what this operation does is it does an element-wise add of the 5 elements in source 0 DSD with the 5 elements in source 1 DSD, and it writes them to DST DSD. Now, remember, I said earlier that we have limited SIMD capability, and we can actually do 4 half precision adds in a cycle. So we can do this operation here, this f_add_h, right? We perform these operations for however many cycles it takes to complete. We can do this 5 element-wise add in 2 cycles. The first cycle will do the element-wise add of the first 4 elements of source 0 and source 1 and write to the first 4 elements of DST. The second cycle will take the 5th element of source 0, add it to the 5th element of source 1, and write it to the 5th element of DST. And again, by 2 cycles, that means I am grabbing from memory, I am performing the add operation, I am writing back to memory. Now, there's one other important thing about DSDs, which they're also the way that we send data to our PE's router. It's the way that data leaves our processing element. So in this case, we have what's called a fab out DSD. What this declaration is saying right here is that if in a built-in operation that uses this DSD, if I use this DSD is going to send data to my router along the color named output color. So this fMovH built in right here is going to take the 5 elements referenced by destination, by DST, DSD, which are the 5 elements in DST, and it's going to send them up to the fabric, and then they will travel along whatever routing we've given to output color. So all in all, what this task here does is it does a 5-element-wise add of source 0 and source 1 and writes it to the DST array. And then it takes those 5 elements that DST, DSD references, and it sends them up to the fabric, where then they will travel off to neighboring PEs along the routing given by the color output color. So DSDs are really a unifying concept that brings together complex memory reads and writes on the processing element, along with reads and writes to our fabric. So I'm gonna quickly give a code snippet before I move in to a couple more details about the SDK and then some recent applications, including a really interesting one out of a researcher at A&L. So I have a little code snippet here. Programs that are written in CSL have kind of 2 pieces always. There's a layout code block, and then you have your individual codes for the processing elements. So this layout code is not something that lives on any one processing element. It's kind of a global file that tells the compiler how I want my colors to be set up on all of my processing elements, and what code file I want to compile for each processing element. So in this case, I have some file named peprogram.csl, which I'll show on the next slide. This set rectangle call is saying that the program that I'm writing is going to use a 2x1 block of PEs. So that's 2 columns and 1 row. So just 2 PEs side by side. Each of those PEs is going to have the file peprogram.csl assigned to it. These are some parameters that were assigned to that file. I said that parameters had to be defined and bound at compile time. So we have 2 parameters I'll show you in this peprogram.csl file. One for the color that we're going to operate on, and one that's this little flag called PEID, which we'll use to make the behavior of the program different depending if we're on the left PE or on the right PE. We then have this set color config call, which is telling our program how we want this color, which we've named my color, to be routed. So here on the left PE, we are going to receive up our ramp and transmit to the east. And then our right PE is going to receive whatever wavelets are sent out from our left PE along this color, are going to receive from the west and transmit down our ramp. So you can see these 2 colors are kind of connected here. My color on the left PE is set up to send out from our PE and to the east, and our right PE is set up to receive along this color from the west. Okay, so what is this peprogram.csl, the actual piece of code that we compile onto the PE, look like? So this piece of code here is an extension of the last piece of code I showed you. Apologies, I meant to remove this set local color config here, so ignore this last line. But we see you have 2 types of tasks. We have a rec of task, which is a data task, so a task that receives from wavelet, and then we have this task called send task, which is a local task. So at compile time, if we are the left PE, we will activate this send task. So this send task will begin running immediately on the left PE. What this send task does is, using a fabout DSD, it sends the number 5 out to the fabric along the color rec of color, which means it travels out of our PE and then to the east. And then that PE will be, or that wavelet will be received by our right PE along the color rec of color, where it will activate the task rec of task, and then global value on the right PE will be set to the value 5. So when this program is done executing, the right PE of the two PEs will have global value set to the value 5. So that's a little bit of a flavor of the language and the programming model. With our SDK, we provide lots of examples, lots of introductory tutorials, and increasingly more complex example programs, including some full-on finite difference codes. We have a code that does a solution of the wave equation. We have some interesting hypersparse sparse matrix vectors, some very simple FFTs, a lot of common linear algebra routines like a conjugate gradient or Cholesky decomposition. We have lots of really interesting example programs shipped with our SDK, and these are also all publicly available in a GitHub repository. So I want to move into talking about what people have done with these sorts of tools and what people have done with the programming model, applications beyond our PyTorch stack. So one application which really squeezed as much as possible out of our incredible memory bandwidth what was this application we worked with and our partners with Calst. I believe Natalia briefly mentioned this one yesterday. This was actually a Gordon Bell finalist last year for seismic processing. The core feature of this application is that it required doing lots and lots of teeny tiny matrix vector products, which we can do really well because of our incredible memory bandwidth. And in fact, when we distributed this application on 48 CS2s, we got memory bandwidth across those 48 CS2s that was comparable to what this same application gets on Fugaku, which has the highest memory bandwidth of any supercomputer. It has less peak flops than Frontier, but it's the highest memory bandwidth. And our memory bandwidth across these 48 CS2 systems is actually higher than Frontier's memory bandwidth on this problem. So this was a really neat problem. There's a link here in the slides to the paper. Another partner that we've worked quite a bit with, and this is one that really takes advantage as well of our incredible memory bandwidth, is with Total Energies. So Total Energies in their first major paper with us achieved a speed up of 228x over an A100 on a stencil algorithm for solving essentially a wave equation with a source perturbation. So this is kind of a key kernel in a lot of seismic imaging workloads. This is the kind of thing as well where the scaling comes into play. We do on this one particular problem size 228x what an A100 did, but you couldn't just keep cluster together 228 A100s and achieve the same performance, because then there are strong scaling issues with communication between the edges of your domain. They've gone on to do quite a bit more work, including a finite volume flux computation, which they presented at SC23. They also have another paper coming up at SC24, which is another seismic algorithm. And they have some internal proprietary code they use to do a reverse time migration, which is a key workload in seismic imaging. So a researcher at ANL also did some really neat work in a completely different domain using the SDK. And this was work on Monte Carlo particle transport, particularly on the macroscopic cross-section lookup kernel. So their first paper demonstrated 130x over an A100 over a highly optimized CUDA version of this kernel. Last week at the conference on the physics of nuclear reactors had a new paper which actually reached 180x over an A100. This is another case where you couldn't just cluster together 180 A100s and get the same performance. So this is kind of a neat application of thinking about, you know, how you take your problem and map it to the architecture. So the key idea of this cross-section lookup kernel is when you're doing a Monte Carlo simulation of particle transport for nuclear physics, you basically you have some material that's composed of a bunch of different nuclides. Each of those nuclides has a different density that it contributes to the overall material. And if you have a particle that's traveling through your material, there's all sorts of reactions that it could do, right? You know, it could cause a fission, a fusion. There's all sorts of things that particle could do. And those different types of reactions and those different types of reactions are called reaction channels. So what they did here with this kernel is that if you have a whole bunch of particles that you want to know how they're going to interact with your material or calculate the probability of how they're going to interact with your material, they start out by essentially randomly distributing particles across the CS2. So each one of these blocks is a processing element. Then they shuffle the particles until they get to their correct energy band. So each of these particles has a given energy, and they communicate the particles up and down the grid until they reach their correct energy. And then once they're at their correct energy, they do this round robin between all the nuclides, and they calculate, okay, what is the contribution for each nuclide to the probability that I do a fission or a fusion reaction. So there's this really neat way to take this key kernel, the main limiting kernel in Monte Carlo particle transport, and map it to our architecture in a really unique way. That team at ANL has written 2 really cool papers about this, which I highly recommend. This first one's on archive. The second one, it's public, but I'm not sure if it's publicly available yet. One more thing I'll quickly mention. So we're going to be talking more about this after ISC next week. This paper is not yet available publicly, but we've also had a team working on an application out of a sister lab, actually a few sister labs of ANL, which has been interested in doing the embedded atom model for molecular dynamics. So the embedded atom model is a molecular dynamics model. It's meant for metallic systems. It doesn't have a lot of like point-to-point long range interactions. This was a really cool application in that it really showed the power of strong scaling on the CS2. On an 800,000 atom simulation of tungsten, material made of tungsten, they were able with a single CS2 to reach speeds 2 orders of magnitude higher than you could do on the entirety of Frontier, simply because of strong scaling limits with a problem of this size on Frontier. So this was a really neat result. So I'm wish I could talk more about it now, but look out for some announcements about this work at ISC, because I think that this is another great example of the power of this architecture for a whole host of other problems. Okay, so one last slide. If the SDK is something that you're interested in using and exploring our architecture at a lower level, please reach out to me. I meant to put the link here as well. I'll make sure that a version of the slides go out that has also the click link. So the SDK is of course available at ANL, so you can actually run your code on ANL's systems. But we also have a singularity container which we freely provide to anybody, which has the simulator inside of it, so you can start, learning about the SDK and our programming model, using that simulator on any x86 compute resource. If you have an Apple Silicon Mac, you can run it on the Apple Silicon Mac through an emulator. We also have a developer community at discourse.cerebras.net. If you want to run on ANL systems, I have some notes on the SDK website about how to do so. And of course, we also have this public SDK examples GitHub repository. And this actually is the URL to go to access the SDK. The SDK simulator. Yep.
Quick question: the appliance mode, running on the appliance and running on the ANL system in appliance mode, how hard is that? Does that involve any configuration changes, or is it just something that
they can be submitted just like you submit PyTorch jobs?
Yes.
The only difference, the only notes here are that there are some slight tweaks you have to make to your Python host code. So if you've written a program to run with a Singularity container, there's a couple of imports that you have to change in the Python host code. But everything else is the same. So it's not like it requires any administrator tweaks to the system in any way. I mean, you submit it as a Kubernetes job, like any other job.
All right, thank you.
But yeah, but I would suggest, if someone is just starting getting learning, it's a lot easier just to get the container and a compute resource that has Singularity or Aptainer and just mess around in the simulator at first. And then, when you're ready to run on the real machine. So John Tram's papers were all using through appliance mode, ANL's machines, then hop on and submit jobs to the appliance.
Does the simulator use multiple cores or not?
You mean does it simulate multiple PEs, or does it use more than one core? Like,
yes, does it use multiple cores? If you have like a bunch of cores on your machine, will it run faster?
Yes. Currently, it's actually hard coded to use 5 threads, but the next release is actually going to give a user controllable flag to set the number of threads that it uses. And we're also working on backend like distributed memory support for the simulator, so that you could even in principle run the simulator on like multiple x86 nodes, 20 x86 nodes or whatever, and simulate not super efficiently, but like kind of efficiently a very large wafer, potentially even up to the size of a real wafer. But that's in progress. But in terms of multi-threading, it does have multi-threading.
Thank you.